Hello guys, welcome to Hardcoder. In this video, we are going to see the Leetcode problem number 110, balanced binary tree. Let's get into the question. So the problem statement it is straightforward. It is you will be given a binary tree's root. You need to determine if it is height balanced or not. So let's dive into the approach. So let's copy the sample this case. So first of all, we need to define the problem. So it's nothing but first of all, you need to know about the binary tree. Binary tree is nothing but a node which has only maximum it will have two nodes as child. So it will have only two nodes as child. It can have one child which can be right. If we consider this node as a parent, it can have the parent can have two child which is mentioned in this case, or else it can have a single child to the right or to the left, or parent can have, this is a parent, can have no child. So these are the four possible ways for a node in a binary tree. So this is the condition for a binary tree. Let's see what the balanced binary tree is. Before that, we'll see what is height of a node in binary tree. So height of a node is nothing but a leaf node, that is a parent without a children is called a leaf node. The node, that is which is a leaf node, will have a height of 0, and the parent node, the parent of a leaf, let's call it, if it is leaf node, the parent of a node will have height of 1, which will be the height of a node is nothing but the height of the maximum height of its children plus 1. So when we consider this test case, we'll determine the height of each node. So it's nothing but the height of leaf node is 0. So let's mark 0 for every leaf node, and height of the parent will be maximum of child nodes. So maximum of child nodes 0, 0 for 20. If we consider the node 20, the maximum is 0. So the left child has height 0 and right child has height 0, and plus 1 will be 1. So height of 20 will be node 20 will be 1, and height of 3 will be maximum of left and right child, that is 1 and 0. 1 and 0 will be 1 plus 1. So the height of node 3 will be 2. That's it guys. So this is all about the height of a node in a binary tree. So let's see what is balances. So we'll edit this. So balance of a tree. Balance of a tree is nothing but height of left child, that is height of left child minus height of right. This should be uh, the absolute value. Let's call it amps. Let's have a function amps. Absolute value should be less than or equal to 1. It can be 0 or 1. Less than or equal to 1 means it should, and the balance should be 0 or 1. This should be the case for balance. So each node in the binary tree should be balanced. This is the condition for the problem. So let's dive into the approach for this problem. So we'll edit this. So approach for this problem would be, firstly we'll find the height of each node. find height of each node, and the next step would be check the balance of each nodes. So this is the approach we are going to utilize in this problem. So firstly we'll find the height of the each node. So how can we find the store the height of each node? We can use a map to store node and the corresponding height, which will be integer. The height of node will be integer, right? So we can use a map, but it will take a space complexity of big O of n. So how can we reduce this? So we can just replace the nodes value by their heights. So firstly we'll find the we'll use DFS to find the height of each node. So firstly we'll go through 3 and we'll go to 2, I mean we'll go to 9 and find the height of 9. So height of 9 will be 0, and we'll reach here and we'll move to 20 and we'll move to 15, and the height of 15 will be 0 and height of 7 will be 0. So what will be the height of 20? So height of 20 will be max of left and right. So left and right will be 0, 0 plus 1, which will be 1. So height of 20 will be 1, and height of 30 will be max of 0 comma 1, which will be left is 0 and right is 1. That is the height of 20 is 1. So max of 0 and 1 is 1. So 1 plus 1, which will be 2. So firstly we'll calculate the height. So if we see the newly formed tree, which will be replacing the 3 by 2 and 20 by 1 and 50. Yeah, when we see, I'll draw it into a new diagram. So it will be 2 0 1 0 and 0. So after finding the height of t, so first step is over of this approach, and we'll go to the second step. Second step will be we'll check for balance in each node. So firstly we'll check for root node. So root node balance will be 0 minus 1, which will be minus 1. When we take absolute value, it will be 1, which is less than or equal to 1. So this case is met. So finally next we'll go to left child. So left child it will have a 0. So left child height of left child will be 0 minus 1 and minus 1. No, let's consider the null values have minus 1 value. So minus 1 will be yield 0. Minus 1 plus 1 will yield 0. So balance of this node is 0 and balance of this node is 1, and balance of this node is 0 minus 0, which will be 0, and balance of this node will be 0 and this node will be 0. So we can see that every balances are less than or equal to 1. So the tree is completely balanced. So we'll return true. This is the condition. So let's dive into the coding section. There you will get the complete knowledge of how to approach these two steps. So let's dive into the coding section. So firstly we store heights. So we'll have a helper function to height of root, and finally we'll return check balance. So there are two helper functions. Firstly we'll write the helper function for store heights. We'll have a node is root, and if so we'll return the height of the corresponding rate. So we'll have return type as int. So if root is null, we'll return minus 1. So leaf of a null node will be minus 1, leaf of leaf node will be 1. So uh, we'll say root dot values other max of store height of root dot left, comma store height of root dot right. plus 1, and finally we'll return the current root dot that is the firstly we'll find the roots left node's height, and next we'll find the roots right node's height, and we'll add the one with them, and finally we can store this in the roots value, and we'll return the root value which will be the height of the current node. So correspondingly in the recursive call we'll store height of each nodes. So finally we'll write the hello Java next, which will be return boolean value. Firstly, if root is null, we'll consider it as balanced, or else we'll check the balance of the current node. So balance will be nothing but if we'll firstly need to calculate the balance is nothing but left height math dot absolute of left height minus right height, right? So what is left height? Left height is nothing but if root dot left is null, we'll return -1. We'll have it as left height as -1, or else root dot left dot val. So same goes to right height. Root dot right is, if root dot right is null, we'll consider its height as -1, or else root dot right dot val. So it will be height of the each node. So finally we'll find the balance, and we'll return balance equal to less than equal to 1, and check balance of root dot left and check balance of root dot right. So what we are doing here, so we'll check the balance of the current node, and we check the balance of left node and check the balance of right node. So let's check with the sample test case. What mistake have we done? To store heights. It's working fine for sample test case. So let's check with the other test cases. It's working fine. Let's submit it up. Accepted. And the time complexity of approaches order of n, and space complexity is order of log n. So why this log n? Because you are going to use a stack space up to log n, which will be let's call it as height of the tree. So this is the space complexity. This will be height of the tree. We'll be going to the depth of the current node. When we have a skewed binary tree, we'll go completely till the end. So which will be height of the tree. So thanks for watching this video. Have a great time. And the approach for this problem will be recursion. So that's all about this video. Have a great time. Thank you.